bits matrix. Okay, so what does it mean? It means that the entry nm is just a function of the difference n minus n. Okay, so this means that, for example, all the elements on the diagonal are the same, and all the elements on the line above the diagonal are also the same, but possibly different from those on the main diagonal. And so, for example, one may be curious what this looks like for the wrapped Gaussian that we just saw. Turns out there's the matrix DP is also kind of as a Gaussian kind of the elements, the off-diagonal elements fall in a Gaussian way, right? So decay in a Gaussian way when you move outside of the main diagonal. Okay, good. So of course we want to use channels to send qubits, for example. So we want to put the quantum capacity, and I think I need to introduce that to you, right? So this is the scheme for the quantum capacity. So so you see, well, of course we want to send a system M by encoding it with an encoding map En, and then applying the channel n times in parallel, and then decoding the message. And we want the corresponding error that I denote by epsilon n to go to 0. Okay. And the number of qubits sent per channel used, this is called an achievable rate. And the supremum of all achievable rates that I, also denoted by R, unfortunately, as the reference system. Sorry about that. So, but the supremum of all achievable rates, that's called the quantum capacity of the channel. Okay. It's a very important quantity and very difficult to compute. And another thing that we may want to do with channels is to establish entanglement between sender and receiver. Okay, so this is there's another figure of merit for this task, which is the two-way assisted quantum capacity. Okay, so the picture is a little different in this case because you can basically apply the channel still n times, but the thing you apply it between, say, n, so that is Alice and Bob spatially separated. Of course, you are allowed to apply the channel n times, but between every application of the channel and the next, you are allowed to apply an LOCC, so a local operation and classical communication. And so after n uses, you're supposed to get a state which closely resembles a certain number of qubits. Okay. And the two-way quantum capacity is, of course, the maximum number of qubits per copy per use of the channel, that you get in the asymptotic limit with vanishing error. Okay, so there are also other figures of merit, for example, the private capacity or the two-way private capacity that are related to how much secret key you can generate, and also the strong converse exponents. Okay, so these are defined in just the same way, but you require the error in the transmission just to stay below 1 instead of going to 0. So it's a weaker requirement, so you get larger figures in principle, so larger quantities. So this Q dagger, for example, this is a strong converse quantum capacity. This is in principle, it may be larger than the quantum capacity. Okay, and the problem, of course, we're going to tackle here is that of computing all of these capacitors for the bosonic dephasing channel. And this problem was posed by Jiang and Chen in 2010, and also investigated by this paper that I mentioned before by Akan and Mancini, Memazadeh. And yeah, it's been open ever since. And the main result of this talk is that under a very mild condition on the probability or regularity condition on the probability distribution P, which is this equation phi, which means that basically one of its Renyi entropies has to be finite for some alpha 0 larger than 1. If that holds, which is the case in most practically interesting cases, you can compute all of these 8 capacitors. They all coincide, and they are given by this very simple formula in equation 6. Okay, just log 2 pi minus the differential entropy of the probability density P. And okay, so in particular, this means also that even if you allow unlimited classical communication between sender and receiver, you still cannot do better than the quantum capacity. So the Q2, so the quantum capacity assisted by two-way communication, it's just the same as the quantum capacity. And also it tells us that generating secret key, the private capacity, is just as hard as generating entanglement. Okay, while in principle it could be easier. Okay, and the other thing to observe is that this formula here, this equation 6, the right-hand side of equation 6, is just if you want to interpret it in an information theoretic way, it's very simple. It's just the relative entropy distance between the probability distribution P and the uniform probability distribution on the interval, which is minus pi pi. Okay, good. So very simple formula. And it's also very easily generalizable to the multimode case. And I won't delve into this multimode case anymore because it's just really kind of the proof is really analogous, but I want to show you the formulas. So, well, this is the general channel. You have possibly correlated phases across many modes. And then you get an exact kind of the same formula, basically still the relative entropy distance between P and the uniform probability distribution, which now takes this form. And again, you have some finite Renyi entropy regularity condition. Okay, so, and this, it turns out that this is, so for finite dimension, the dephasing channel, it was known what its quantum capacity was, and it's indeed a formula which looks very much like this one, with the exception that you have a discrete entropy instead of the continuous entropy or the differential entropy. And this formula was found in this paper by Pirandola, Laurenza, Ottaviani, Banchi, 2017. And so you can, I mean, our formulas are kind of a generalization, but we will see the proofs are kind of a bit different. Well, quite a bit different because we're in infinite dimensions. So you have to be more careful, way more careful. Okay, so and the example for the wrapped Gaussian, very simple plot. That's the plot you get if you plug in this the formulas that I gave you for the case of the wrapped Gaussian. The case in which the phase phi is just a random, a normal random variable, basically. You can also derive, you can derive an exact expression in this case, but also approximate formulas that are very useful. For example, for gamma, which is kind of small, you get this universal dependence. Well, okay, yeah, exactly. 0.6 plus this log of 1 over gamma, basically, half of that bits per channel use. And when gamma is very large, you get an exponential decay of the quantum capacity, which also makes sense because, of course, when gamma is very large, the off-diagonal elements of the input state get very much depressed. So they get multiplied by a very small number. So you basically lose almost all coherence. So the quantum capacity and all capacities actually decay exponentially. This was already shown in this paper by Mancini and collaborators that I showed you. But here we find the actual formula. Okay, so they show that there was some exponential decay. Okay, so some proof ideas. Okay, so let's keep things simple. Let's say that we want just to compute the two quantities. So the quantum capacity, unassisted, and the two-way assisted quantum capacity, okay? Since, of course, the quantum capacity is always smaller or never larger, it's enough to prove a lower bound on the quantum capacity and an upper bound on the two-way quantum capacity. Okay, if you find that they're given by the same formula, then you're done. Okay, so A, lower bound. Well, the lower bound is very simple in principle, kind of. The idea is very simple because we just use the one-shot coherent information, okay? So one copy coherent information, that's enough. So that's the coherent information for those of you who are wondering. So it's a quantity that is very fundamental in computing the quantum capacity. And it's actually, its regularization coincides with the quantum capacity, as the Lloyd-Shor-Devetak theorem tells us. And okay, so basically you have to plug a state. You construct basically a state on AA prime, and then you send the system A prime over the channel. And then you get a state AB, and then you compute this combination of entropies for that state. So to compute a lower bound on the supremum, you need an ansatz for the state psi, right? What ansatz do we make? Well, just the maximal entangled state over the first D Fock states, okay? Well, oh, sorry, K should start from 0 and then D minus 1, that's summation. And of course, the idea being that we want to make D tend to infinity, that we want a very large entangled state. Okay, so, but for now, let's keep D finite. Okay, so denoting by this TPD, the D times D upper left corner of the Stirplitz matrix that I introduced before. So you see immediately that the coherent information is given by this kind of entropic looking expression of this finite matrix. Okay, so if you want to go further and compute this trace, you could ask yourself, can I compute the eigenvalues of these operators, in particular of the operator TPD? Well, it's a matrix. In principle, of course, you can compute the eigenvalues numerically, but do we have analytic expressions when D is large? Well, in certain cases, yes. And it's very instructive to look at this case. For example, if the probability distribution P is supported onto set of angles that have this form. So you see kind of that rationally dependent from pi. So if the probability distribution is just supported on just those angles, so you can actually see that this Toeplitz matrix is actually circular. Okay, so it has one further symmetry, so it's invariant under shift. So it commutes with the shift operator. Okay, the one that sends every vector of the canonical basis into the following vector cyclically. And so for circular matrices, it's very well known how to compute the eigenvalues because they're diagonalized in Fourier basis, and so discrete Fourier basis. And so in this way, you can actually compute the eigenvalues. It's very simple. You see immediately that they are actually given by this pk times d. Okay, so if that is the case, then you can easily compute this trace, and you get actually an expression which we very much like. And so now the problem is, can you somehow, so you see this is very special for just those probability distributions that have this kind of support condition. But when d goes to infinity, you can actually see that the set of angles becomes dense somehow. And so you expect that this condition becomes not so restrictive, right? Because you can simulate any probability distribution by, probability distributions of this form if d is sufficiently large, intuitively. Okay, so basically we want to generalize this discrete probability distribution to the continuous one. And how do we do this? Well, there's a theorem in asymptotic linear algebra called Zegos theorem that allows you to do just that. Okay, and applying this theorem is what requires us to use this regularity condition that I was describing before with the Renyi entropies. And by a swift application of the theorem, you can compute the limit of this expression when d goes to infinity, and you get exactly what you should get. Okay, so this is actually, so like for an arbitrary probability distribution P, this matrix here will not be circular, of course, right? So it will be just a Toeplitz matrix. So you can't apply this formula straight away, but you somehow want to apply it in the limit. Okay, and this is exactly what Zegos theorem tells you. This is it's a highly non-trivial statement in itself, but this is basically, I hope it makes sense why it should work intuitively, something like this at least. Okay, so far so good. What about the upper bound? Well, Q2 requires an optimization of a very complicated protocols. This, protocols intertwined with LOCCs. So, but the key observation is that this channel actually is what is called teleportation simulable, which means that using a channel is actually, so if I give you one use of the channel to use it, whenever you want, this is exactly the same resource as a copy of the choice state of the channel. Okay. And see, the choice state is what you obtain by sending across the channel the maximum entangled state. And this equality works only in the limit when the maximum entangled state is sufficiently big. Okay, so basically what I mean is that whatever Alice and Bob can do on the left by having one use or multiple uses of the channel, they can do on the right. So having one choice state or multiple choice states of the channel. And the reason why this is non-trivial is that the choice state on the right-hand side is a static resource, while the use of the channel is a dynamic resource, right? So basically, on the right-hand side, you have already committed to the input of the channel. You say, okay, I don't care what the input will be. For now, I just send the maximum entangled state, and then everything will be fine. But in principle, these two things are not the same, because on the right-hand side, you committed to a state, while on the left-hand side, you are not committed to a state. You can send any state that you want. Okay, so in principle, the left-hand side, the use of the channel will be more powerful than the right-hand side. But for this special channel, for a family, wide family of channels, the two actually are the same. Okay, so and teleportation simulability implies that the two-way quantum capacity is actually upper bounded by the distillable entanglement of the choice state in the limit. And so then you do some tricks, for example, upper bounding the distillable entanglement with the relative entropy of entanglement. Okay. That's a very well-known fact in entanglement theory. And then so you want to find yet another upper bound, which is, well, okay, since relative entropy is defined as an infimum, I plug in an ansatz for the state and I get exactly this expression. It turns out if you plug in the right ansatz, and then you see, once again, Zegos theorem in the limit gives us the correct expression. Okay, so that basically concludes the proof. And well, it's remarkable that the Zegos theorem actually appears twice, one for the lower bound and one for the upper bound. Great. Okay, so conclusions. Right. We gave an exact formula for the capacity for all of these 8 capacities of the bosonic phasing channels, right? All of the private and quantum capacities, both both unassisted and two-way assisted, and also both strong converse and weak converse. And the formula generalizes a capacity formula for finite dimensional dephasing channels, right? But the proof is actually, it's way more delicate because it requires a lot of for example, Sager's theorem in asymptotic linear algebra, and also a bit of care with infinite dimensional systems. And where there are some open problems that I'd like to advertise. First of all, we don't understand the energy constraint capacities for this one. I would very much like to understand those. And also, there are related models of noise across optical fibers that are more difficult to investigate, and it would be really good to be able to say something more about these channels. For example, another very typical phenomenon is photon loss, of course, across an optical fiber. And for example, you get a more refined model of noise if you add photon loss to the picture. So not only dephasing, but also photon loss. And also for that one, we don't know how to compute the capacities. And with that, I'd like to thank you.
Thanks for the wonderful talk. And any questions or comments?
I have a question.
Okay, please.
Please.
Hey, Ludovico, nice talk. If this regularity condition is not satisfied, does that give rise to a channel where the capacities are separated?
We don't know. I just don't know how to do the computation, because you see, like this Sager's theorem, actually, if you use the original version, that's not good enough. You have to use some, so like people have put forth all sorts of refinements, right, for this theorem. So like basically there is a 50-year long research line on this, and like of course, like most of this is devoted to removing regularity conditions. So this was kind of the weakest regularity condition that we could find in this paper by Serra Capizzano, actually lots of Italian guys. So it's kind of the weakest regularity condition that we could find that guarantees that we can apply this theorem. Otherwise, we don't know. So it may be that the mathematicians have to work a little harder, or it may be that there is a separation, God knows. I would expect that in any reasonable case, there won't be separation, but
There would not be.
There would not be. Just wild.
Okay. It's a strong conjecture, no?
Well, okay. I mean, I don't know. It would be surprising, right? I mean,
I don't know.
It's one of those things like, jumping on a plane that flies thanks to the difference between Lebesgue integration and Riemann integration. These kind of things don't pop up.
Okay.
Somebody said I would never fly on a plane that flies thanks to the difference between Lebesgue and Riemann integrations. So like, I mean, I would expect that regularity conditions don't play a major role here. It's kind of, but I don't know.
Okay.
Can I comment, Ludovico?
Please.
So we do have an alternate proof based on Golovkin-Stashevsky, right?
Right. That's right.
So perhaps the upper bound, we didn't include that in the paper, but I think the upper bound would still hold. Would we need the regularity condition for the upper bound to hold using that method? Because the regularity condition is for the Zago theorem, right?
Correct. Possibly not, but yeah, Golovkin and Stashevsky also that's an infinite dimension. So at some point you have to, yeah, okay.
The idea was that we can think of the upper bound as a comparison between the channel of interest and the channel that completely dephases, right? And
correct.
But
how do you compute the Golovkin-Stashevsky relative entropy between those two?
The point is that there's a data processing argument that underlying these channels are these distributions, and it's simply a comparison between P.
Right. Yeah, exactly. Okay.
Uniform over 2 pi, uniform over the interval minus pi to pi.
Yeah, now I remember, yes.
I think it would not be limited by that.
Yeah, I can't see right now exactly. Maybe I think you're right. Yeah.
but that's perhaps offline.
Mm.
Can I quick question for your comment, Mark? Are you saying that in that case, all of the capacities would have the same upper bound again, and then therefore no separation? Is that
I'm saying
The
that
lower bound is not.
they would have the same upper bound, but maybe there would be something with the lower bound, because the lower bound still relies on the Zago theorem, and that requires the regularity condition.
I see. Yeah, thanks for the extensive answer. Interesting.
I have a question, and I'm wondering whether I'm not familiar with the continuous case, but just wondering whether the channel is the type of channel that just generate maximum correlated states.
This one, yeah, well, I mean, it did. I mean, like if you send in a state which is, say, yeah, sure, kind of the choice state is maximally correlated. Let's put it like that, like this.
So it always create, so since the entangled state, it always generate maximum correlated state, right?
So if the initial state is maximally correlated, then the final one is maximally correlated. Correct.
No, I mean, because you can define maximum correlated state independent of the ancillary system, right? Because you can freely rotate its basis such that the two bases are the same, right?
Sure, but if the initial state is not maximally correlated, the final one won't be maximally correlated in general.
Ah, okay, okay, no. Okay,
but
thanks.
if the initial it respects maximal correlation. So like if the initial state is maximally correlated, then the final is also maximally correlated.
Okay, because I mean, from the result, I can see that for maximum correlated state, the coherent information is always equal to the relative entropy of entanglement.
Correct. Correct.
Okay,
Yes.
thanks.
That's very much underlies what's going on here. Yes.
Okay, thank you. Any other questions?
I have a question.
Oh, please.
And it's not strictly related to the presentation, but how many non-Gaussian, let's say physically motivated quantum channels are there for which we don't know the quantum capacity? Because this is my fault, but I thought that the phasing channel was a solved model in that sense. So how many others quantum channels in continuous variable non-Gaussian are there for which we don't know the quantum capacity?
Oof, well, okay. For example, this one that I wrote here on the slides.
Yeah, the loss. Okay.
Yeah, photon loss plus the dephasing, the one we don't know. Well, I mean, there are all sorts of families for like of channels that are Gaussian dilatable, so what they call Gaussian dilatable. So, like for example, sending a beam splitter, mixing the input signal in a beam splitter with a fixed state in the environment, which is not necessarily Gaussian. So this is also another kind of natural family of channels, but these are not like super important in applications. I can think of many others.
Your co-author today stressed how important that model is in applications.
Yeah, okay.
Right? Sorry.
So which model?
Where you're like changing. the
Sure. Right.
Yeah.
No. Okay. Of course. Right. I mean, for some crazy states, crazy environment states, this is not, yeah, I mean, like, it's not, of course, like if you engineer it, that's another story. But if you want just a state that a channel that you find naturally in the environment, that's gonna be Gaussian most likely. I mean, unless it's a very short fiber or a very active environment somehow where active optical components do something, or you engineer it to be this way. Yes.
Okay, thank you.
You're welcome.
Any other questions or comments? If no, let's thank Ludwig again. Thank you.
Thanks a lot, guys.
Okay, you can turn off the slides.
Are we doing the breaks or are we just going right into?
We should probably go right into it because of the delay, right?
I'm fine with that. Yeah.
Right.
Should I start sharing?
So Felix, you're the speaker, right?
Yes.
Yes, please proceed the next talk.
Ah, okay, our next speaker is Felix Lietje. He will talk about bounding quantum capacities via partial orders and complementarity. Please.
Thanks a lot, Dong. Thanks for having me. Thanks to the organizers. Thanks also as well for accommodating the different time zones. That's very, very helpful. So this is joint work with Christoph Hirche and appeared on the archive and will also soon appear in the IEEE Transactions on Information Theory. And the goal of our work was to bound quantum capacities using partial orders and complementarity, where complementarity refers to the complementary channel. Because Ludovico talked about this, I will be short here. We talk about quantum channel capacities. So a quantum channel is a CPTP map between algebras of operators on Hilbert spaces. And we look at it as a noisy communication link. And then this quantum channel can have different capacities depending on the type of information I want to send through it. For the in order to send quantum information or equivalently to transmit entanglement, I look at the quantum capacity of the channel. And this here is exactly the same figure that Ludovico drew, only his was much prettier. So I'll be very short again. So the idea is just that Alice shares entanglement with some inaccessible reference. She can encode her share using some encoding map into the input systems of an IID channel. So here, this is the same channel acting everywhere. That channel sends the quantum input states to Bob, who decodes them to get some system B tilde. And the hope is that this will be close to the initial entangled state with respect to some suitably chosen figure of merit. And if in the asymptotic limit I can make this perfect or faithful, then the highest achievable rate of these protocols is the quantum capacity of the channel. The other capacity we look at is the private capacity, where I now want to send classic information in a way that is secure from the eavesdropper. So here Alice has some classical random variable that she wants to encode in a quantum state ensemble. And these ensembles are collections of states defined again on n input systems to the channel. Then they're sent through the channel. And now Bob receives the states and wants to decode them to some classic information, x hat, that should be close to x. But now we want to assume that Eve actually doesn't learn anything or doesn't learn anything useful in the asymptotic limit when she also receives the environment from these channels. So the V here refers to the isometric extension of the channel, which maps the input system to the output system and some environment system E. For both of these quantum channel capacities, we have formulas. So for the quantum capacity, this is the quantum capacity theorem, which expresses the capacity in a regularized formula. And the underlying information quantity in this regularized formula is the so-called coherent information that I obtained by taking a pure bipartite state psi on A and A prime. Those are both isomorphic copies of the input system to the channel. in general. And then I send the A prime system through the channel to get a bipartite state on AB. And then of that state, I take the coherent information, which is down here, the entropy of the B system minus the joint entropy. For our purposes, it's useful to look at a slightly different formulation of this in terms of difference of mutual informations. So here I take a classical quantum state. So it's a separable state where the X system in this rho XA state is classical, so it's diagonal with respect to a specified basis. And what's important here is that in this optimization of these two mutual information terms, I only look at those CQ states where the quantum part is pure, conditioned on the classical label. And I will be consistent in the talk by always indicating such CQ states with XA. Okay, so whenever you see an X in a classic quantum state, it means it's a CQ state where the quantum states are pure. And again, here we obtain, we send the A system through the channel, through the isometric extension, actually, and then we look at these two mutual informations, one for Bob and one for the environment. And so, optimizing this over all CQ states gives us the channel information. And then for the actual capacity, what we do is we evaluate this not just for one copy of the channel, but for a growing number of copies. And then we normalize, and then we take the largest of all of the ones that we see. Alternatively, we can take a limit n to infinity. It's the same thing. Okay, that's the quantum capacity. For the private capacity, the situation is similar. So it's again a regularized quantity where now the underlying information quantity is the so-called private information. And this is now a straightforward generalization of the query information that I wrote down before, because now we again optimize this difference of mutual informations, but we allow arbitrary quantum state ensembles. And keeping in line with this notation choice, these mixed CQ states will always be denoted by U in the classical system. Okay, so rho UA corresponds or denotes a classical quantum state with arbitrary ensembles. So the rho AU states here, the states conditioned on the classical label U, are mixed in general, whereas before they were pure. Okay, then we optimize over all those to get the channel prime information, and then we do this again for a growing number of channel copies, normalize, take the supremum or the limit, and we get the private capacity. And from writing the two information quantities like this, it's immediately obvious that the two are bounded by each other. So because the optimization, the prime information contains the optimization for the coherent information, it's always at least as big as that. And then when you regularize, when you apply the coding theorems to this inequality, you regularize and normalize and take the limit, you then in a straightforward way get that the capacities satisfy the same inequality. But of course, you can also see the capacity inequality in an operational way, because whenever you can generate entanglement using a channel, you can always turn this into secure classical information transmission. But this is an entropic way of seeing this inequality, if you will. Okay, so we have the capacities, and as a warm-up and kind of like the main way of explaining our idea, we want to show how the capacities of a channel can be bounded by the capabilities from an information theoretic point of view of the complementary channel. Okay, so the theme of our work is that the complementary channel tells us something about the capacities of the channel. And as the motivating example, I'm actually taking other capacities, the ones that I didn't talk about. I want to be very quick here. So we actually, it's easy to see this on an entropic level for the classical capacities and information quantities. So the underlying information quantity is the Holevo quantity or chi quantity, where we just take CQ states and just look at the mutual information just for Bob, and we drop the Eve term. And regularizing this gives us the classical capacity of the channel, which is basically classical information transmission where we drop the security criterion for private capacity. And then there's also this entanglement assisted version where I also give to the sender and receiver unlimited entanglement that you can use in the N and decoding. This is just basically making this CQ state into a fully arbitrary quantum state, bipartite quantum state, where we send one half to the channel and then we look at the mutual information. And it follows in a straightforward way from looking at the entropic formulas that we have these inequalities here. So the whole information, because it basically drops the mutual information with Eve, it's always at least as big as the query information. And then regularizing, apologies, this one shouldn't be here. Regularizing the same holds then for the capacities. And we can also do a similar thing for the entanglement assisted capacity, where we get a factor of 2 here, basically because of teleportation and superdense coding. And now you can show using these entropic formulas that we can actually bound these information capacity quantities again by the left-hand sides plus some error term. And this error term is exactly a information quantity or capacity of the complementary channel. Okay. Again, I'm calling this a warm-up and not actually a result, because it's really easy to just derive this using the entropic formulas. And we will spend a little more time looking at these for the quantum and private capacity, but this set of inequalities already conveys the gist of our results in a certain sense. Okay. Of course, here the last inequality here is really just by analogy, because the entanglement assisted classical capacity is a very nice capacity where we don't need any bounds because we can just compute it efficiently. Okay, but this is just to demonstrate the analogy that it also works for this capacity. Okay, so to look at the quantum and private capacity versions of these inequalities, we need to look at partial orders of quantum channels. One that already exists for quite a while in literature is that of degradability. So a pair of channels is called satisfies the degradability order, or n is greater or equal than m in this degradability order, if and only if there's another quantum channel D called the degrading map that degrades n to m. And the D maps, of course, in a compatible way between the output of n and the input of m. This is a slight generalization actually of what's usually used in literature for degradable. So originally this has been defined in the following way, that n is called degradable if n can be degraded to its complementary channel. And dually, we call the channel anti-degradable if the complementary channel can be degraded to the channel. And so a channel is degradable if and only if its complementary channel is anti-degradable, okay, and vice versa. And we know that these partial orders imply certain statements about the capacities and information quantities. So if n is a degradable channel, then we know that the quantum and the private capacity actually coincide. So there's no separation between them. And furthermore, they're actually given by single letter formulas, namely they're all equal to this single letter channel query information. And then furthermore, in that case, you can actually also efficiently compute this. And if the channel is anti-degradable, then we know that they all, again, coincide, but they're actually always equal to 0, which you can prove using an entropic argument, but you can also prove this operationally using a version of the no-cloning argument. So we already see that these orders here imply something about the capacities. And then the work of Watanabe was to generalize these orders by working directly with the capacity quantities. And so he defined the following terminology. A channel n from A to B is called less noisy if the complementary channel has 0 private information. If you want to write this out in entropic terms, this means that if you take CQ states rho UA, then the mutual information of U and E can never be larger than the mutual information of U and B. This needs to hold for all CQ states. And degradable channels are an example of this, okay? Then you can now, instead of the information quantity, go to the capacity quantity, which means that you need to regularize. So you need to basically do this for all number of channel copies. So we say a channel is regularized less noisy if the private capacity of the complementary channel is 0. Or alternatively, in terms of entropies, you need to satisfy this inequality of mutual informations But now this is actually on n input systems, and the n needs to be arbitrary. And then there's a third version, which is a little newer, which is called the fully quantum less noisy order. And so here we call the channel fully quantum less noisy if you basically make this CQ state relation here fully quantum. So you now say, instead of a CQ state, I take an arbitrary bipartite quantum state. I send half of it through the channel. I look at the two mutual informations between A and the environment and A and Bob. And then it needs to satisfy this entropic inequality here. This actually has also been defined in literature by Mark Wilde and collaborators. They call this the entanglement-assisted private information, where you just turn this into an entropic quantity where you now optimize over all input states. Okay, and then the fully quantum less noisy definition is that this needs to be zero. Okay, so this is a couple of orders or definitions for channels in terms of the private information and capacity quantities. And now we can all apply them to the quantum capacity quantities. And it's basically all by making things pure. Okay, so in the same way as before with coherent prime information. So we now call the channel more capable if the complementary channel has zero coherent information. And again, this means that now this mutual information equality needs to be satisfied for all CQ states. Rho XA, remember now the convention, X means that these are CQ states where the individual states are pure, the individual quantum states. Yeah, so this is a strictly weaker condition than what we had before. We then can again regularize this. So we say a channel is regularized more capable if the quantum capacity of the complementary channel is zero, which now means that we need to do this, we need to satisfy this inequality for all number of channel copies. But again, restricting to pure state quantum ensembles. And then we can also make this fully quantum again in the same way, where instead of the CQ states, we now take pure bipartite states, but arbitrary. And then we again have to satisfy this inequality of mutual informations. And there you can also define a corresponding information quantity, which you don't want to call QE because it's not the entanglement-assisted quantum capacity, but it's this quantum version of this entanglement-assisted private information that we talked about before, where you take a bipartite pure state, send half of it through the channel, and then you look at the difference of the mutual informations and optimize. Okay, and Watanabe proved about these classes of channels a remarkable set of results that generalize what we know about degradable and antidegradable channels. So Watanabe proved that if n is more capable, then that always means that the Fourier information and the prime information are always equal to each other. And yeah, okay, that's it. If the channel is regularized more capable, then the same holds for the capacity quantities. And if n is regularized less noisy, it means that they're actually all equal to each other, and there cannot be any superadditivity. So here, if a channel is regularized less noisy, then the capacity quantities are equal to the information quantities, and those are single-letter quantities. Okay, and so degradable channels are an example of the third class here, and antidegradable channels as well, of course. You should contrast these results with the results by Davis-Sutter et al. A couple of years later, where they kind of made some of these results approximate. And so they introduced this notion of epsilon degradable or approximately degradable, where we call a channel epsilon degradable if the complementary channel is not quite the same as, cannot quite be obtained by degrading the channel, but you can get epsilon close to it when you optimize over the degrading map. And the closeness here is measured in terms of diamond norm, which is a useful metric on quantum channels. And if we have an epsilon that satisfies this criterion, then we can write down these inequalities for the capacities that basically tell us that the superadditivity, or the gap between the single added quantity and the regularized quantity, is bounded by a function, this delta 1 of epsilon and the environment dimension here. And you can do the same thing with the private capacity and also the difference between information quantities. It's going to be different functions, but what they all have in common is that when you keep the environment fixed, but you take the epsilon to 0, then they all go to 0, which then reproduces the results we know about degradability and antidegradability. And we want now, in a different way, to turn Watanabe's results and his classes of channels into an approximate form. And so, if you look at the definitions from before, it's kind of obvious how to do this, because you just you let the inequalities be violated, but only up to a certain parameter of epsilon, and then that's going to be that approximation parameter. So, for example, we call the channel epsilon more capable if this mutual information inequality is only violated up to a certain epsilon. Okay, and alternatively, you can say that the channel information of the complementary channel can be positive, but not too big. Okay, so it's bounded by this epsilon. And then in prior work, Christoph with Daniel Stilkwanza and Camille Sousset proved that if we have these approximate partial orders for the quantum channels, then we can again get approximate versions of the results by Watanabe. So for example, for epsilon more capable, whose definition is written out here, this now limits the gap between the coherent information and the prime information by this parameter of epsilon. And we have similar results for epsilon regularized more capable, which bounds the separation of the two capacities. And then the other ones here, I don't want to read them all out to you. You can look at them in paper. Problem with that is only that this epsilon, the definition is a little unsatisfying, maybe because you don't really know what that is. And so we wanted to simplify this in the work with Christoph now. And it's based on a very simple observation, actually, that you can just take as the epsilon, you can just take the capacity or the information quantity of the complementary channel. Okay, and then immediately these bounds turn into a rather nice form. So for example, for epsilon regularized more capable, if we just choose the epsilon to be the quantum capacity of the complementary channel, then every channel is epsilon regular more capable. Yeah. So it sounds a little vacuous, but it actually leads to very nice capacity bounds that are all phrased in terms of capacities itself. Okay, so this is our main result, or one of our main results, that we have this set of inequalities where the information quantities and the capacities of a channel are bounded in terms of these corresponding quantities for the complementary channel. And you can actually also prove them somewhat directly without going through this approximate partial order business by just using the entropic formulas in a clever way. And let's take maybe a closer look at these bounds. So the first two bounds here tell us something about how much quantum and private capacity can be separated, right? Because we saw before that the left inequalities are always true, either based on entropic or operational arguments. And then the right-hand sides bound the capacity in terms of the left-hand side plus some error term. And the error term is just given by a quantity of the complementary channel. Okay. And so, for example, here we have this very nice inequality that the private capacity is upper bounded by the quantum capacity of the channel and that of the complementary channel, which I find very pleasing in some way. And the other two inequalities you can understand as inequalities that bound the amount of superadditivity you can get. Okay, so we have channels for which there's a strict gap between the channel information and the capacity quantity. And then our bound tells us that that gap is controlled or bounded by this entanglement assisted prime information. For the prime information, it's a little more complicated about. And for example, one thing that this bound gives us is a new insight that if I have a channel that has zero capacity for both the channel and its complementary channel, then this bound implies that the private capacity also has to be zero. I will come back to that later, okay? Another cool thing is that this actually gives us numerical bounds on private capacity from numerical bounds on quantum capacity. So this is somewhat like an annoying problem that for the private capacity, there's not too many useful bounds that you can actually compute. Whereas for the quantum capacity, by now, there's a large body of work that has some that you can, like, for example, using semi-infinite programming. And so now this gives you an easy way of doing this for the prime capacity of a channel. Okay, it's sometimes not very useful, but sometimes it is useful, and I'll also come back to that later. Okay, another thing that we do in the paper is that we actually apply this all to the static case of states. So here, instead of a channel, we now have just a bipartite state share between Alice and Bob, or rather IID copies of it. And then we can again look at what's the largest quantum key or key that they can distill from copies of this bipartite state. And if we only allow one-way classical communication from Alice to Bob, then this is the exact state analog of the private capacity of a channel. Okay, and so we call this the one-way distillable key. And if we want to distill entanglement from the bipartite state instead of secure key, then the corresponding quantity under one-way LLC operations is the one-way distillable entanglement. And those are denoted by K with the forward arrow and D. For operational reasons, we again have this inequality here. And there's also underlying information quantities, and then those are regularized versions of these information quantities. But I didn't want to show too many entropic quantities. Okay. And in terms to show, in order to show our results here, we adopt the somewhat non-standard notation that we call the complementary state rho ABC, just to have the analogy with the complementary channel. But it really is just taking a purification of your mixed state and then tracing out Bob to get a state on Alice and Eve. So this is just rho AE, but we choose this more suggestive notation, maybe. Okay. And then we can again define these partial orders or approximate partial orders by limiting the one-way distillable key or entanglement of the complementary state. Okay, and so we call them epsilon more secret if we have this inequality, and epsilon more informative if we have the equality for the one-way distillable entanglement. And then we prove in the paper that we have the exact, like we have an analog of our capacity bounds now in terms of these distillable entanglement and distillable key quantities. And they have the same form, basically. So again, for example, here, this third one is the exact, sorry, the fourth one, the third and the fourth one are the exact analog of the bounds that I showed before for quantum and private capacity. And so these operational bounds are, again, they have the same benefits as before. Okay, so they give you new insights that the key of a bipartite state is zero if you cannot entangle either to Bob or to Eve. And it also gives you a way of numerically estimating them with just using bounds on the distillable entanglement. And the situation here is similar to the channels. So we have more bounds for the distillable entanglement than for the key, I think. Okay. If I have a little bit of time left, I want to go through some open problems. So one thing that is basically open since the work of Watanabe is to ask whether the class of degradable channels and regularized less noisy channels is actually separated. Okay, so as a reminder, a regularized less noisy channel has a complementary channel with zero private capacity. And a degradable channel is one where the complementary channel is obtained by degrading the actual channel. And from this, it follows that the complementary channel has zero private capacity. So degradable channels are always regularized less noisy, but it's not known whether there is a regularized less noisy channel that's not degradable. Okay. And what we found in our paper is a curious connection to the superactivation of private capacity. So as a reminder, superactivation means that you take two channels that each have zero capacity, in this case private capacity, but when you use them together or jointly, that thing now has a strictly positive private capacity. Okay, and we don't have an example of superactivation of private capacity yet, but if there is one, then that actually implies that the two classes of channels are strictly separated. So this, at least in our opinion, kind of like is one more motivation to look for superactivation of private capacity. And so the question is, why don't we have that example? Because we now understand the superactivation of quantum capacity fairly well, I would say. And the problem is that for superactivation, you either, like in a way that we understand it, at least, you either need two different classes of zero capacity channels, or you need one class that is not closed under tensor products. Okay. And the only class of channels with zero private capacity that we know is that of antidegradable channels, which is closed under tensor products. Okay. So if you take two antidegradable channels, then the tensor product will again be antidegradable. So that thing can't have positive capacity, private capacity. And so then based on our bounds, we now had an idea. Okay, what if we take a channel that is PPT to both Bob and Eve? So both the channel and its complementary channel are PPT, which means that they have zero quantum capacity. Because then by our bound, this would imply that they have zero capacity also for private information transmission. And so let's call these channels by PPT channel. We weren't really sure whether there was terminology there. And we thought, okay, maybe there's an interesting example of something that has actually, that is interesting and satisfies this condition. Bad news was that shortly after we put this out, there was a proof that these channels are actually not very interesting because they're always entanglement breaking. So this is a very nice paper by Alexander Müller-Hermes and Sadvik Singh, a couple of weeks after we posed this question, who proved that every bi-PPT channel is entanglement breaking. And of course, entanglement breaking channels you can never use in a superactivation result because they will just break every entanglement. However, I am still interested in this setup because what we did in numerical studies is that we found approximately bi-PPT channels. Okay, so those are channels that are almost PPT to both Bob and Eve. But they are actually non-trivial in the sense that they have strictly positive channel information and therefore strictly positive capacity. Okay, so they cannot be entanglement breaking. And then actually also applying our bound for these channels then also shows that our capacity bound can in certain situations be useful as a numerical tool as well. Okay, because the bound that we get from our capacity bound is actually better than the private capacity bound that you can evaluate that's in the literature. So I'm very interested in these examples, and maybe we can find maybe that those can help towards a superactivation of private capacity. That would be very cool, I think. And with that, I would like to conclude. So we found, or we derived these operationally meaningful bounds on quantum and private capacities of both channels and states in terms of the complementary object, the complementary channel or the complementary state. And the proofs rely on these approximate partial orders. You can find the paper in the archive and soon in the transactions. And with that, I would like to conclude, and thanks for your attention.
Okay, thanks, Felix, for the interesting talk. We have time for a quick question.
I have a question.
Okay, please.
This is Mark. Thanks, Felix, for your talk. It's very interesting. I might have asked you this already. Is there any hope to apply this kind of reasoning to the two-way assisted capacities?
Yes, you have asked this before, and the answer is still I don't know. This is much harder.
One might hope for
to prove
as an analogy to your. I think a very interesting band, like you said, is the private capacity is bounded from above by the sum of the quantum capacity of the original channel and the complement. And one might hope to get that kind of thing for the two ways.
Yes, this would also, I mean, it wouldn't surprise me if someone has also thought about this in the state case,
right?
With distillable key and distillable entanglement. Yeah, I agree. It's a good question, and I would let me conjecture that similar bound should be true also for two-way.
Oh.
It would be strange if they weren't, I think.
Okay, seems worthwhile to think about.
Okay, let's thank Felix again. Thank you.
Thanks a lot.
Oh, Debbie Leong raised her hand to ask a question.
Yes, thanks for that opportunity.
Okay.
Hey, David.
Well, I have some concern about the situation with two-way assistance, because the notion of degradability will not play as much of a central role anymore, right?
Yes.
And so I just don't see how, I mean, it's not just the fact that we have no capacity formula, but the whole, the heart of all these results seem to not really hold in that setting.
I agree that the orders would have to be adapted to this for sure.
Is there even a notion of degradability in the two-way assisted setting?
A notion that similarly implies additivity, you mean? Or like,
Yes.
I don't think so.
The main tool is this teleportation simulation trick where everything simplifies. But I don't know. Yeah, it's true. I mean, the complement. Yeah.
Right. Well, let's talk more at the break.
No, it's a very good point, Debbie, that obviously the way this is built up makes use of these relations between channels that only have relevance in the one-way setting, in a sense. And so for a two-way, you would have to go through the corresponding one. I mean, somehow the role of anti-degradability is a little bit played by, no, you can't say that, but I mean, PPT is relevant in the two-way case, right? But PPT is not an order. It's defined, or it's not defined in terms of the complementary channel. Let's put it that way.
Right.
It's an intrinsic property, so to say. I don't know, maybe there's a link to quantum broadcast channels as well, a little bit. But maybe Mark knows more about this. I don't know.
I don't. We can continue in the breakout room.
Yeah, for sure. Thanks for the questions.
Thanks.
So any question? No. Okay, if no, let's thank Felix again. And shall we continue or we have a break?
Please continue.
Okay. So.
Hi, everybody. Okay.
Oh, okay.
Okay, I guess you should be able to see my screen.
Yes.
So please stop the recording and record start.
Okay.
Okay.
I guess, can you hear me?
Our next speaker is Stefano Chessa. He will talk about resonant multi-level amplitude damping channels. Please start.
Okay, thank you. Okay, as said, I will talk about resonant multi-level amplitude damping channels, which is a work that I did together with Vittorio Giovannetti, who is now my former PhD supervisor at Scuola Normale Superiore in Pisa, in Italy. And we posted this work a couple of months ago on the archive. But before dealing with this, I will give a very, very brief introduction of the concept in quantum communication that I'll need, but it will be very brief since already Ludovico and Felix spoke about this. And then I will talk about multi-level amplitude damping channels. And this section will be more or less a replica of the lightning talk that I gave right here at Beyond IID a couple of years ago. And this, it was just 5 minutes, so it won't take too much time. And it makes a very linear, natural introduction to the central discussion about resonant multi-level amplitude damping channels. So as promised, let's start with the very, very basics of quantum channels in quantum communication. I will skip this, the part about the protocol of one-way quantum communication, because again, Ludovico and Felix already talked about this. I will just stress the fact that any noisy quantum channel can be expressed as with what is called the Stein spring representation, which is a unitary interaction between the Alice input system, input state, and a sufficiently large environment in a pure state. And making the long story short, the figure of merit to quantify the capability of the noisy communication is given by the current information, which is, as we've already seen today, is the difference in phenomena entropy between the output of the quantum channel and the output of the complementary channel. And the current information is important because through that we define the quantum capacity, which is the maximum achievable quantum information rate transmittable per channel use. And the issue with this expression, as you probably know, is that the maximized current information is in general not additive. And so the computation, the actual computation of this expression for the quantum capacity is practically infeasible in general. But this is what makes the task of finding quantum capacities challenging and interesting. But luckily for us, there are properties that Felix already described, like degradability and anti-degradability, that simplify the task. In particular, degradability, we say that a channel is degradable if you can express the complementary channel as a composition between the channel and a suitable quantum channel, here represented by delta. And David Arkanshaw showed that for a degradable channel, the maximized current information results to be additive, and so we can switch from the regularized formula for the quantum capacity to a single letter formula for the quantum capacity, which is clearly a big simplification of the task, since we have to maximize the current information only over a single instance of the Hilbert space. And anti-degradability goes the other way around, in the sense that we can say that a channel is anti-degradable if we can express the channel as a composition of the complementary channel together with a suitable other quantum channel called here lambda. And due to a simple no cloning argument, we can say that if a channel is anti-degradable, the quantum capacity of this channel will be trivially zero. And so, since what we'll do is to introduce and define two new classes of channels, multi-level amplitude damping channels and resonant multi-level amplitude damping channels, you can guess what would be our strategy in order to analyze their quantum capacities. So we'll go see where these channels exhibit degradability or anti-degradability and there find their quantum capacity. So we can switch to, firstly, to the multi-level amplitude damping channels that are amplitude damping channels in the higher dimensional scenario. And we define those simply by generalizing the qubit amplitude damping channel picture that basically represent the relaxation process in a qubit of the excited state 1 onto the ground state 0, depending on a damping parameter gamma, which is a real parameter ranging between 0 and 1. And as you all know, as well as all other quantum channel, we can express the action of the qubit amplitude damping channel by expressing what is called the Krauss set, which is a set of operators. And in the case of the qubit amplitude damping channel, this set is composed by two operators, one a diagonal one and an off-diagonal one that tells you how the channel works, in the sense that it maps the level 1 onto the level 0, depending on a damping parameter. And then applying the Krauss operators in the Krauss set to the input, a generic input density matrix, we get the action of the qubit amplitude damping channels. And we can see that it transfers a fraction of the excited population, the diagonal excited population from the excited state onto the ground state. And it dumps the off-diagonal coherences with a multiplicative term, clearly depending on the damping parameter, Okay, and regarding the information capacities, some of the information capacities associated with the qubit amplitude damping channels were firstly approached by Giovannetti and Fazio some years ago in 2005, and in particular, concerning quantum capacities, they showed that the large class of qubit amplitude damping channels is antidegradable for damping parameter ranging between 0 and 0.5, and degradable ranging from 0.5 to 1. Actually, for our definition of the damping parameter would be reversed, in the sense that this would be the anti-degradable region, this is the degradable region, but the message stays the same. And as we saw before, the anti-degradable channels will have capacity, quantum capacity trivially 0, and the degradable side of this channel will have an expression for the quantum capacity that will be a single letter formula, and so we will be able to compute exactly the quantum capacity of the channels. So for the qubit amplitude damping channels, the quantum capacity is known exactly on the entire range of the damping parameter. Okay, so as we said, what we did is to generalize this picture from the qubit to the multi-level scenario, so to qubits systems. And to do so, we generalized the Krauss set, basically, with still one diagonal Krauss operator, and now a number of off-diagonal rank 1 Krauss operators that it's equal to the number of decay processes that we have in our multi-level amplitude damping channels. And in this sense, you can see that enlarging the underlying Hilbert space makes also the complexity of the process grow, in the sense that by taking more levels, we have combinatorically more possibility to decay from higher levels to lower levels. And by studying the properties of this new class of channels, we found out that they are closed under channel composition, in the sense that if we take two different multi-level amplitude damping channels, each one with its own array of damping parameters, then their composition is still a multi-level amplitude damping channels with an array of damping parameters given by this composition rule, which is not important to remember now, but we have to remember just the fact that they are closed under channel composition. The first reason is because we'll use this closure under composition to exploit data processing inequalities for the quantum capacity. And the second reason is that for resonant multi-level amplitude damping channels, this fact will not hold in general. So just keep in mind this. Now, going to the quantum capacity analysis, the issue with the generic multi-level amplitude damping channel is that, let's say, a dimensional independent approach was not available. I mean, at least I wasn't able to find one. So we started with the first non-qubit, non-trivial example, which is given by the Q3 example. So three-dimensional Hilbert space. So with three levels, we have three possible decay processes. And as we said before, to each decay process corresponds an off-diagonal rank 1 Krauss operator. And by the application of Krauss operators to a generic density Q3 density matrix, we get the channel action that we can see is has a behavior really similar to the qubit amplitude damping channel, in the sense that we have a transfer of population from higher to lower levels and a damping of the diagonal coherences given by a multiplicative factor depending on the magnitude of the damping parameters. Okay, then going to the meat of the quantum capacity analysis. The issue with already Q3 multi-level amplitude damping channel is that they can be proved to be in general not degradable, in the sense that thanks to this nice result from Qubit, Sky, and Smith, what they showed was that given a Q3 to Q3 channel like ours, a channel phi, then if phi is degradable, then its Choi rank is at most 3. But since the Choi rank is equal to the minimal number of cross operators that our channel needs, and in our case, as we saw before, is 4, we already know that for a generic Q-tip multi-level amplitude damping channels, we don't have degradability. We can prove that these channels are not degradable. And for what we said before, we're not able to express in a simple closed formula the quantum capacity for this kind of channels. So what we did to address the problem was to simplify the problem by killing at least one of the Krauss operators in order to reduce the Choi rank. And so by killing 1 or 2 Krauss operators, we get a subclass of double decay rate Q-tip multi-level amplitude damping channels and a single decay rate subclass of multi-level amplitude damping channels. So at least now with Choi rank lesser or equal than 3, we at least can hope these channels to be degradable. So we went for the study of the degradability and anti-degradability conditions and found out that these channels exhibit degradability or anti-degradability in extended region of the damping parameters. And so there, in degradable and anti-degradable regions, we were able to compute exactly the quantum capacity. The nice thing that turned out is that by exploiting the data processing inequality, if we got exploiting the closure under composition rules, we were able to extract upper bounds that compared, coinciding with efficiently computable lower bounds, allowed us to express exactly the quantum capacity also for multi-level amplitude damping channels in regions where these are probably not degradable or not anti-degradable. And this is a nice fact for 2 reasons. The first one is that there are very few instances in the literature of channels that behave in this way, for which the quantum capacity is known also in non-degradable and non-anti-degradable regions. And the second reason is that also Q-tip resonant multi-level amplitude damping channels will exhibit a similar feature. So we can directly, now that this introduction is closed, directly jump to the central part of this talk, which is given by resonant multi-level amplitude damping channels. And to understand how we constructed this new class of channels, we'll take a step back and go to analyze the 2 possible channel representation that we saw in this talk. The first one is given by the Stein-Spring representation. As I said before, the Stein-Spring representation tells you that the action of the channel can be seen as a unitary interaction between the input from Alice and an environment in a pure state. And the other one is the Krauss representation, where you express the Krauss set and apply the Krauss operators in order to get the action of the quantum channel. Now, in some way, we could say that the Stein-Spring representation is somewhat more physically explicit, in the sense that in the unitary matrix that you have here, you encode the physics that relates the evolution of the state from Alice to the environment. While the Krauss representation is a little bit more abstract, in the sense that the physics is somewhat hidden in the shape of the Krauss operator, and you just apply them to get the expression for the channel. But this is more or less what we did for the qubit and the multi-level amplitude damping channels. We just took a Krauss set that, again, for multi-level amplitude damping channels has this structure, a diagonal operator, and then a number of diagonal operators for each possible decay process. But equivalently, we could have just tried to specify the Stein-Spring representation. And to do that, we would have needed just to specify the possible transition that occur between the system from Alice and the environment, mediated clearly by the unitary evolution that the Stein-Spring representation gives you. And again, this picture, let's call it a physical picture, is more direct, because you can see immediately what kind of processes relate the system to the environment. But also it's more interesting because by looking at this transition, this explicit transition, you can also start trying to play with it in order to understand what happens if you change something in this unitary matrix. And in particular, you can engineer your transition by tuning the damping parameters or choosing different levels to which your initial level will transition in order to get something different. And this is what we did to get what we call then resonant multi-level amplitude damping channels. We just played with the transitions, and what we asked ourselves was in particular, what happens if we constrain the environment? We constrain it in the dimensionality. You can see here that it's three-dimensional, and we constrain it in the energy spacing, in the sense that in this case now we are considering just system and environment with equally energy spacing, in the sense that these levels, these energy intervals are resonant, and from this resonance comes the name resonant multi-level amplitude damping channels. And you can see that even though the transition that you see in the Alice systems are the same as the multi-level amplitude damping channels, now the environment is different, because again it's constrained in energy and in dimensionality, but also now it's not like for the multi-level amplitude damping channel where every decay process excited a single different excited level in the environment. Now you have that two different processes in the system from Alice excite the same level into the environment, the same first excited level into the environment. So now the environment is not able anymore to discriminate which one of these two decaying processes happened in Alice system. Okay, and translating this into the Krauss picture, we have still a diagonal operator, a rank 1 of diagonal operator, but now you can see that we have that two of the multi-level amplitude damping channels of diagonal and rank 1 operators have been merged into a single Krauss operator, which is now rank 2. And these two processes that have been merged into the same Krauss operator are exactly those ones that the environment is not able anymore to discriminate. Okay, and clearly these differences in the physical picture and the Krauss picture will reflect also onto the channel action. But again, I want to stress the fact that even despite these two channels onto the Alice system describe something similar, they overall describe a different physical picture. Here we have a 4-dimensional, in the Q-Tree multi-level amplitude damping case, a 4-dimensional environment system. Here we have a 3-dimensional environment. Here there are no constraints regarding the energy spacing of the levels. Here we have resonant levels in the system and in the environment, and also the number of Krauss operators switches from 4 to 3. And again, this translates into the action of the resulting resonant multi-level amplitude damping channel, which is still an amplitude damping channel, in the sense that you still have a transfer of a portion of the populations from diagonal populations from higher levels to lower levels. You still have a damping of the coherences in these two elements of the density matrix given by just a multiplicative factor depending on the magnitude of the damping parameters. But now here on the element corresponding to the 0, 1 element in the density matrix, which corresponds to the space 0, 1 in the environment that cannot anymore discriminate the decaying processes, you have this mixing of coherences, which clearly is a completely different behavior that with respect to the one that you have in multi-level amplitude damping channels. And while this difference could seem relatively small in the sense of the action, the overall action of the channel on the density matrix, you have that this small difference changes the, let's say, macroscopic behavior of these channels. We've seen that multi-level amplitude damping channels are closed under channel composition, and irrespectively of of the input damping parameters. This doesn't hold anymore in general for resonant multi-level amplitude damping channels. In general, a composition of two resonant multi-level amplitude damping channel is not anymore a resonant multi-level amplitude damping channels. The composition is closed only if given gamma prime and gamma second, the arrays of damping parameters of the channel phi gamma prime and phi gamma second, then their composition is closed only if the damping parameters follow this constraint, which again is not necessary to, it's not much important to remember, but we just need to remember that again, this small difference in the shape of the action of the channel changes the macroscopic behavior in the damping in the parameter space by breaking the closure under composition rules. So this is not the only difference that we get for resonant multi-level amplitude damping channels from this difference in behavior for the coherences. Also, the analysis of degradability now changes because as we saw before, the degradability for the multi-level amplitude damping channel was forbidden by this theorem from Kubidur-Sky and Smith because of the Choi rank, basically, because for acute multi-level amplitude damping channel, we had a Choi rank equal to 4. Now, since we merged to cross operators, we have a Choi rank equal to 3. So now, even for, let's say, a complete resonant multi-level amplitude damping channel, which is with non-zero, all three possible damping parameters non-zero, we have the possibility to have degradability. And by studying the degradability regions and anti-degradability regions, we find out that nearly half of the allowed volume, and for allowed I mean the region of the damping parameters that gives you a completely positive map. About half of this volume is or degradable, the yellow zone here, or anti-degradable, the blue region. And so in these regions, we can exploit the fact that the coherent information can be expressed with a single letter formula and compute exactly the quantum capacity. But again, as happened, and okay, here you can get, these are slices of this degradable region, depending on the parameters gamma 2, 0, gamma 2, 1, and gamma 1, 0 for different values of gamma 1, 0. And you can see the evaluation, the exact evaluation of the quantum capacity. But again, as happened with the multi-level amplitude damping channels, by exploiting data processing inequalities where the composition rules hold, we were able to derive upper bounds that coincided with efficiently computable lower bounds that allowed us to compute exactly the quantum capacity of these channels in regions that are not degradable or anti-degradable. And again, this is a very nice feature because this adds the class of resonant multi-level amplitude damping channels to the number of examples for which we know exactly the quantum capacity, even without having degradability or anti-degradability. So to conclude, what we did is to introduce this new class of multi-level amplitude damping channels, resonant multi-level amplitude damping channels, which are, again, physically, they describe a different physical picture with respect to the multi-level amplitude damping channels case. We show that these channels can be degradable or anti-degradable for all three, in the Q-tip case, all three damping parameters different from 0. In those regions of degradability and anti-degradability, we were able to compute exactly the quantum capacity and also the private capacity. I didn't mention this, but the analysis for the private capacity is exactly the same. And then we were able to compute exactly the quantum capacity and the private capacity for some of these channels, also outside of degradable and anti-degradable regions. And that is more or less all for this. Thank you very much.
Well, thanks for the great talk. Any questions or comments?
I have a question. This is Mark.
Sure.
Thanks for a very interesting talk. Regarding your last point, on this slide, Q and CP outside the regions, are
Okay.
the capacities equal?
Yes. I mean, yes, they are.
Yeah, that's very interesting. I mean, your class of channels is very physically motivated well. So it's nice to have this result when they're physically motivated and not degradable.
Yeah, I mean, we already commented this last Beyond IID, but then I forgot, and I don't know what is the list of channels for which this holds. I guess the platypus channel has been added to this list, but then I don't know how many other channels we find with this kind of feature, and I mean for discrete variables clearly.
Are there any other questions? Okay, if no, let's thank Stefano again. Thank you.
Thank you. Bye.
Bye.
So is my screen visible to everyone?
Yes. Sorry.
Naqib.
Okay.
Yeah. Yeah.
Okay. The next speaker is Naqib Ahmad Wasi. He will talk about the commitment capacity of classical quantum channels. So please start.
So hello everyone. So I would like to thank the organizers for giving me this opportunity to present this work here. So this is a joint work with Professor Masahito Hayashi, and as the name of and as the title of my talk says, I will be talking about the commitment capacity of classical quantum channels. So before discussing the technical details of the problem, so let us first discuss the problem intuitively. So consider the following scenario where there are two parties, Alice and Bob, and they are playing a game of chess for several hours, and then they realize that it's very that it is very late in the day and they have to stop the game, and they plan to again start the game in the next morning. So in this scenario, there is a problem because if Alice plays her turn before stopping the game, then Bob will have the entire night to think of his next move. So that would give him an unfair advantage. And on the other hand, if Alice doesn't play, she will have the entire night to think about her move. So the question is that, is there a way to get rid of this solution? And one of the, is there a way to get rid of this problem? And one of the solution is that if there is a trusted referee wherein Alice can write down her next step and put it into an envelope and give it to the referee who may announce it in the next morning about her next move. So because we are assuming that the referee is a trusted referee, so Alice will not be able to change her next move once she gives it to the referee, and also Bob will be not able to know what Alice has written in the envelope till the next morning. So actually, these kind of games are played in the Japanese and Chinese chess, and it is actually called a sealed move. So the main question is that, is it possible to accomplish the above task without the presence of a trusted referee? And actually, like this kind of problem was introduced by Blum, wherein he assumed certain computational restrictions on the parties. So we will talk about this problem in the information theory scenario. And this problem was actually introduced by Winter, Nascimento, and Imai in the information theory, like from the information theory point of view. So the problem, as you can see in the diagram here, is that Alice wants to send some messages to Bob such that the messages are secure from Bob until Alice reveals the message to Bob, and she wants to transmit these messages over a noisy channel. So, and we also want to ensure that until Alice tells the message to Bob, Bob should not be able to know what Alice has actually planned to send it to him over the noisy channel. And Winter, Nascimento, and Imai showed that for the case of a classical channel, they showed that if we want these two conditions to be satisfied, that is, Alice should not change her mind while revealing her messages to Bob, and vice versa, that Bob should not be able to know anything about the message until Alice reveals it to him. So under these two constraints, Winter, Nascimento, and Imai showed that the commitment capacity of a classical channel is given by the conditional entropy of X given Y, where X is the channel input and Y the channel output, and we maximize it over the input distribution. So in their paper, they had also claimed that like whatever they have done would also hold for the classical quantum channels. However, they didn't give a proof. They just stated it as a theorem, and we couldn't find a proof of that statement. So me and Professor Hayashi tried to find a proof for this problem, and then we eventually realized that it is not so straightforward to claim such a result for the classical quantum channel, that there are certain issues which I will highlight in this talk. But before that, let me tell you the whole scenario here once again. So for the commitment scheme, there are two steps. So the first step is the commit phase, and the next phase is the reveal phase. So in the commit phase, so suppose Alice wants to send some message M, which is chosen uniformly. So what she does is that depending upon what message she wants to send and her private randomness, she applies some function to her message M and her private randomness, and then she communicates it over the channel to Bob. So what the channel does is that it spits out a quantum state depending upon the input which Alice had sent to the channel. Also, Alice sends a classical input to Bob over this channel. So what she does is that depending upon the message she wants to send and depending upon her private randomness, she applies some function, and in the end she sends some U1 to Bob. So this is the first step of the commit phase. In the next phase, what Bob does is that depending upon the input U1 which Bob has received in the first step from Alice, and the state which Bob has received, Bob tries to Bob measures the channel output, which is WX1 here. So he does this operation coherently using some quantum instrument, and when he measures it, there is some classical output which is represented in terms of V1, and the quantum state after the measurement is quantified in terms of Y1 prime. So after obtaining this output V1, so Bob sends it back to Alice, and then in general in the ith round, depending upon the input received from the Bob, Alice applied some function on her chosen message, her input private randomness, and the input variable from Bob in the I-1th step. And she again does the same thing, applies some function and sends it across to the channel to Bob. So this sort of finishes the ith round of communication between Alice and Bob. But there is one property which we want in our commit phase, is that, yeah. So another thing is that, like in our talk, we will assume that, when Alice is honest, we will denote her operations by, by some collection of operations, which we represent it as A1M. So where A1M represents, Alice's operation for the message M. And similarly, because the Bob applies some POVM, so that is represented in terms of this B here, and if it behaves in a very arbitrary fashion, then we denote it by B prime. So one of the property which we want in our commit phase is that for any pair of the messages in the message set, the joint state induced, like for any pair of the messages, they should be epsilon close. So basically what it means is that this condition would ensure that Bob is not able to get anything about what was the message Alice, which was Alice trying to send it to him. And here we assume two kind of cases. One is passive Bob and the other is the active Bob. So by passive Bob, we mean to say that, Bob is being honest, and by active Bob, we mean to say that Bob is behaving in an arbitrary way and is trying to cheat to Alice. And in the next phase, which is the reveal phase. So in the reveal phase, what Alice does is that she reveals the message to M, and she also reveals her private randomness to Bob. And depending upon this M and Z, which Alice has revealed, Bob applies some decoding POVM on the state which he has. And what we want is that with very high probability, the message M is accepted if both Alice and Bob are behaving honestly. But however, if any of the parties are behaving in an arbitrary way, then we want that, that the wrong message should be accepted with very small probabilities. So here, when we say passive Alice, we mean to say that Alice is only cheating in the reveal phase. That is, she is revealing some arbitrary M from this set. But when we say active Alice, we mean to say that she may also cheat in the commit phase. That is, she is sending some arbitrary input sequences in this CQ channel. So actually, this tuple, which is A1, A2, B, and tau, is called the protocol P with n rounds, where this A1 and A2 represents Alice's operation in the reveal and in the commit and reveal phase, and here B and tau reveals Bob's operation in the commit and reveal phase. And here we define certain parameters. So where here is epsilon is the concealing parameter, that is for any two pair of messages, the state induced should be, like the distance between the state induced should be epsilon close in the L1 distance. And this binding parameter is that, if Alice and Bob behaves in an arbitrary way, then the wrong message should be accepted with probability at most delta. And here this things A and small p represent the thing that, the parties are behaving either actively or passively. So basically our aim is to, find a sequence of protocols such that we maximize the rate of communication as the number of channel users increases, under the constraint that, both these concealing and a binding parameter, they both go to 0 as the number of channel users increases. And the supremum of all achievable rate is called as the commitment capacity of the channel, and we actually define various notions of it in our work. So in particular, we define CA and CP, where A means this active and passive attacks. So actually, like in our work, we observed that it is not easy to discuss a general protocol, and one of the reason is that in the commit phase, once Bob measures the quantum state, that state is just this state just changes to some other state, and because we don't have an handle to it, and also Bob can behave in a very arbitrary way, so in general it is very difficult to ensure both the concealing parameter and the binding parameter go to 0. So to overcome this, we make an assumption that we have we have a condition which we call as the invertibility condition. And basically what it means is that at every step in the commit phase, there exists a CPTP map such that we can recover the original state from the measured state. So for this special case, we define, which is something called the commitment capacity of the case when the parties are have the assumption that where we assume that we have this invertibility condition, and this A and P is again for the active and passive attacks from Alice and Bob. And further, we assume here that this non-redundancy condition, basically what it says is that for every X, the channel output cannot be represented as a convex combination of the channel outputs with respect to other inputs. So this condition is an important condition, but we can actually remove this assumption if we assume that the size of the set over which this X takes values is finite. So under this non-redundancy condition, we show that for the case of non-interactive protocols, and for the case when we have this invertibility assumption, we show that the capacity in these special cases is actually equal to the conditional entropy of X given Y, and we again supremize over the input distribution, which is same as what Winter et al. Proved for the normal classical channels. So actually we arrive at our result in 2 steps. So we first show that for the invertible protocols, the capacity has this upper bound in terms of the conditional entropy. So that is the converse. And then we show a protocol where parties are not interacting. So this non means that there is just one node of communication. There is no interaction between the parties. So in this case, we design a protocol, and we show that we can achieve this rate of which is given by in terms of the conditional entropy of X given Y. So as I told you already that what we mean to say by the class of invertible protocols, basically it means that at every step after the measurement, we are able to get back the original state. So basically it means that that the state induced at the end of the commit phase. So one thing to observe here is that the state induced at the end of the commit phase constitutes of the random variables M, Xn, Un, Vn, and Z, where M is the message being sent, Xn is the input to the channel, Un is the depending upon the message M and the private randomness what Alice is sending to Bob over NYZ channel. Vn is the random variable which Bob gets after the measurement of the quantum state, and Z is the Alice's private randomness. So basically, at the end of the commit phase, the joint states consist of M, Xn, Un, Vn, Z, and the quantum system Y prime N. So where Y prime N is the measured state in the nth step. So basically, when we say that the protocol is invertible, so it means to say that if we apply the above sequence of the invertible maps, then the state induced at Bob's end after their application, we will get back the original state yn. I mean, essentially, that's what it means for the protocol to be invertible. And in this case, like if we call the first state as rho 2 and the second state as rho 3, it can be seen that both the states rho 2 and rho 3 are information theoretically equivalent. So what I mean to say is that the conditional entropy of xn given yn and un with respect to the state rho 3 is same as the conditional entropy of the sequence xn given un, vn, and y prime n with respect to the state rho 2. So with this observation and together with one of the main result of our paper, wherein we show that there exists a function h which will be able to estimate m with very high probability using this xn, un, and vn. So with this so basically, like with this observation that rho 2 and rho 3 are information theoretically equivalent, and with this derivation of this estimation function, we basically are able to show a converse, and basically the converse depends upon the continuity of the von Neumann entropy and the Fano's inequality. And the thing is that showing the existence of H is not so straightforward, and it requires some some non-trivial construction of some special functions. So to discuss more on this H, so one thing to observe here is that we are able to estimate the message M irrespective of the channel output. And we need this property of H because in the quantum setting, the state yn is completely lost in the interactive protocol of the commit phase. So actually, Winter et al. Also used a similar strategy to prove a converse, but their estimation function depends on yn, and they could do it because in the classical case, I mean, even after the n lot of communication, I mean, you don't get like you still have yn, like because classically the state doesn't change whether it's like before and after the measurement. So to take care of this, we had to invent this H, which estimates the message M from xn, un, and vn independent of the output quantum state from the CQ channel. And to prove our achievability result, so basically we show the existence of a code. So basically this 2 raised to n R1 represents the number of messages, and for every message we have a code of size 2 raised to n R2. So here if you see that we have an upper bound of R1 plus R2, and that is basically because I mean to make sure that Alice is not cheating, that is, she is not revealing some arbitrary message to Bob, and if she does that, then that message is not accepted with high probability. But we concentrate on the Hamming distance between any two pair of codes. So this upper bound on the sum rate ensures that if this ensures that that the Hamming distance between any two pair of codes would be bigger than some certain threshold, and because of which Alice will not be able to cheat. And the second criteria you would expect from any wire-type channel kind of result, that basically it is for a concealing property, and it comes from many standard results using a decoupling. So basically, our protocol is based on the quantum extension of a recently, like a very recent paper by Masaito Hayashi in the classical case for list decoding. And basically, we this achievability protocol is the quantum version of his protocol in the classical setting of a list decoding. So I would just now summarize this. So basically, we prove that in the case of non-interactive protocols and in the case of invertible protocols, whether the parties are active or passive, we show that the the commitment capacity is the conditional entropy of X given Y, where and then we maximize this conditional entropy over the input distribution. So you can see more details about this work on this archive link. And yeah, and with this, I would just like to thank you very much.
Thanks for the interesting talk. Any comments and questions? If no, so let's thank Naquib again. Thank you. And let's thank all the speakers.